ये है मैकेनिकल प्रॉपर्टी ऑफ द सॉलिड्स। तो पहले इसका देखेंगे कुछ पी वाई क्यू और फिर इसका देखेंगे एनसीईआरटी। इसमें है कि द बार ऑफ द लेंथ एल, एरिया ऑफ द क्रॉस सेक्शन इज hanging from a fixed support. The length of the bar chain to L1 when mass M is suspended from its free end. The expression for the young modulus कितना हो जाएगा? तो change in the length delta is equal to L1 minus L और एरिया इज इक्वल टू ए, तो फोर्स इक्वल टू एफ इज इक्वल टू एम जी, तो गामा इज इक्वल टू नॉर्मल ऑफ स्ट्रेन बाय नॉर्मल ऑफ स्ट्रेस बाय लॉन्जिट्यूडनल ऑफ स्ट्रेन, तो ये गामा इज इक्वल टू एफ बाई ए डेल्टा एल बाई एल, तो आ जाएगा एम जी एल बाई ए एल वन माइनस एल। आंसर आएगा क्या? आंसर आएगा ऑप्शन सी, एम जी एल बाई ए एल वन माइनस एल। नेक्स्ट है कि two bars are made of the same material and have the same volume. The first bar has a cross-section area A and the second bar has a cross-section area 3A. If the length of the first bar is increased by the delta L on applying a force F, how much force is needed to stretch the second bar by the same amount? तो इसमें आता है कि according to the question area of the cross section is equal to A1, force applied is equal to F1. Increase in the length हो गया delta L from the relation of the young modulus of the elasticity gamma is equal to FL by A delta L. Substituting the value of the for the bar in the above relation we get gamma 1 equal to F1 L1 by A1 delta L. For the bar 2 एरिया ऑफ क्रॉस सेक्शन हो गया ए टू, फोर्स अप्लाइड हो गया एफ टू, अनक्रीज इन लेंथ हो गया डेल्टा एल, तो बाई गामा टू इक्वल टू होगा एफ टू एल टू बाई ए टू इंटू डेल्टा एल। वॉल्यूम भी इक्वल टू एल हो गया, तो एल इक्वल टू भी बाई ए, तो गामा वन इक्वल टू एफ वन भी बाई ए वन का स्क्वायर इंटू डेल्टा एल, और गामा टू इक्वल टू एफ टू भी बाई ए टू का स्क्वायर इंटू डेल्टा एल, तो एफ वन भी बाई ए वन का स्क्वायर पर डेल्टा एल इक्वल टू एफ टू भी ए टू का स्क्वायर इंटू डेल्टा एल। तो यहाँ से अगर करेंगे तो एफ वन बाई एफ टू आ जाएगा ए वन का स्क्वायर बाई ए टू का स्क्वायर, यानी ए का स्क्वायर बाई नाइन का स्क्वायर, तो आएगा 1/9। तो एफ टू इक्वल टू 9, एफ वन इक्वल टू 9 एफ, तो एफ वन इक्वल टू कितना आ जाएगा? एफ आ जाएगा। तो इसका आंसर कितना आ जाएगा? इसका आंसर आएगा ऑप्शन सी 9 एफ। नेक्स्ट है कि द बल्क मॉडुलस ऑफ स्फेरिकल ऑब्जेक्ट इज बी इफ इट इज सब्जेक्टेड टू यूनिफॉर्म प्रेशर पी, द फ्रैक्शनल डिक्रीज इन द रेडियस कितना हो जाएगा? The object is spherical and the bulk modulus is represented by the B. It is ratio of the normal of stress to the volumetric of strain. Then B is equal to F by A delta V by B. तो डेल्टा V by B हो जाएगा B by P, यानी डेल्टा V by B हो जाएगा B by P. Here P is the applied pressure on the object and डेल्टा V by B is the volume of strain. तो फ्रैक्शनल डिक्रीज इन द वॉल्यूम हो जाएगा डेल्टा V by B हो जाएगा 3 डेल्टा R by R, यानी V is equal to 4/3 pi R क्यूब। तो वॉल्यूम ऑफ द स्फीयर डिक्रीज ड्यू टू द डिक्रीज इन द रेडियस, तो डेल्टा V by B हो जाएगा 3 डेल्टा R by R, यानी P by B, तो डेल्टा आर बाई आर हो जाएगा पी बाई थ्री वी, तो इसका आंसर होगा ऑप्शन डी पी बाई थ्री वी। नेक्स्ट है कॉपर ऑफ द फिक्स्ड वॉल्यूम बी ड्रॉन इनटू द बार ऑफ द लेंथ एल व्हेन दिस बार इज सब्जेक्टेड टू अ कांस्टेंट फॉर्स एफ, द एक्सटेंशन प्रोड्यूस्ड इन द बार इज डेल्टा एल, which of the following graph is a straight line? The young modulus given by gamma equal to f into l by a into delta l, तो b is equal to a into l, तो gamma equal to f l का स्क्वायर by b delta l, तो delta l equal to f by b gamma equal to l स्क्वायर, तो डेल्टा एल डायरेक्टली प्रोपोर्शनल टू क्या आएगा? एल का स्क्वायर, तो आंसर आएगा ऑप्शन बी डेल्टा एल वर्सेज एल स्क्वायर, तो आंसर आएगा ऑप्शन बी। नेक्स्ट है द फॉलोइंग फोर बार्स आर मेड ऑफ द सेम मटेरियल विच ऑफ दीज विल हैव द लार्जेस्ट टेंशन व्हेन द सेम टेंशन इज अप्लाइड, तो गामा इक्वल टू एफ एल बाई डेल्टा एल बाई इंटू ए, यानी एम जी एल बाई डेल्टा एल इंटू ए, तो डेल्टा एल इक्वल टू एम जी एल बाई इंटू बाई गामा इंटू ए, तो डेल्टा एल डायरेक्टली प्रोपोर्शनल टू एल बाई होगा, बीजी मैक्सिमम पॉइंट ऑप्शन ए हो जाएगा। अगला है कि स्ट्रेस ऑफ स्ट्रेन कर्व, द थर्मल स्ट्रेस एंड द इलास्टिक पोटेंशियल एनर्जी, तो द स्ट्रेस ऑफ स्ट्रेन कर्व आर ड्रॉन फॉर द टू डिफरेंट मटेरियल सेक्शन बाय it is observed that the ultimate strength point and the fracture point are close to each other for the material X but are far apart for the material Y. We can say that material X and Y are likely to be respectively. The stress of strain curve for material is shown, stress दिया हुआ इधर strain दिया हुआ, this curve यहाँ पर हो गया ये इलास्टिक बिहेवियर, फिर इधर दिया होता है प्लास्टिक बिहेवियर, ये हो गया इलास्टिक लिमिट, ये हो गया अल्टीमेट ऑफ स्ट्रेंथ पॉइंट, और ई हो जाता है फ्रैक्चर पॉइंट। So this curve specify the behavior of the material. For the material, if the distance between the strength point and the fracture point is small, so it is brittle and will break easily on the application of the some extra stress after the point D. For the material Y, if the distance between the strength point and the fracture point is large, so it is ductile material and can withstand for the some extra stress beyond the D. Next, when the block of the mass M is suspended by a long bar of the length L, the length of the bar becomes L plus capital L plus of small l. The elastic potential energy stored in the extended bar है जो कितना हो जाएगा? तो in a stretching bar, the work done against external internal stirring force is stored elastic potential energy in the bar and given by U is equal to W is equal to half into force into elongation, यानी half into FL, तो half into mg into L, यानी आ जाएगा half mgl, तो आंसर आएगा ऑप्शन बी half mgl। अब इसे एनसीईआरटी से तो कुछ नहीं आया है, पर फिर भी क्विकली एनसीईआरटी को इसका देख लेते हैं। इसमें आता है कि in the chapter 6 we have studied the rotation of the body and then realized that the motion of the body depends on how mass is distributed within the body. We restricted ourselves to the simpler situation of the rigid body. Rigid body generally means a hard, solid object having a definite shape and the size, but in reality, body can be stretched, compressed, and bent. Even the approximately rigid steel can be deformed when a sufficiently large external force is applied on it. This means that solid bodies are not perfectly rigid. A solid body has definite shape and the size. In order to change or deform the shape or the size of a body, a force is required. If you stretch a helical spring by gently pulling the string, the length of the spring increases slightly. When you leave the ends of the spring, it regains its original shape and size. The property of a body, by virtue of which it tends to regain its original shape and size, when the applied force removed is known as the elasticity, and the deformation called is known as the elastic deformation. However, if you apply force to a lump or a putty or a mud, then have no growth tendency to regain their previous shape and they get permanently deformed. Such substances are called as the plastic, and this property is called the plasticity. Putty and mud are also close to the ideal plastics. Next is the plastic behavior of the material plays an important role in engineering design. For example, by designing a building, knowledge of the elastic property of the material like the steel, concrete, etc. is essential. The same is true in the design of the bridges, automobiles, ropeway, etc. One could ask, can we design an aeroplane which is very light but sufficiently strong? Can we design an artificial limb which is lighter but stronger? Why does a railway track have a particular shape like the eye? Why is glass brittle while the brass is not? Answer to such questions begin with the study of the how relatively simple kinds of the loads for the forces act to deform different solid body. In this chapter, we will study the elastic behavior and the mechanical property of the fluid which could answer many such questions. फिर आता है stress and the strain. So when the force is applied on a body in such a manner that the body is still in a static equilibrium, it is deformed to a small or a large extent depending upon the nature of the material of the body and the magnitude of the deforming force. The deformation may not be noticeable visually in the many materials, but it is there. When the body is subjected to the deforming force, a restoring force is developed in the body. This restoring force is equal in the magnitude but opposite in direction to the applied force. The restoring force per unit area is known as the stress. If F is the force applied normal to the cross section and A is the area of the cross section of the body, the magnitude of the stress is equal to F by A. The F unit of the stress is Newton per meter square or Pascal, and its dimension is ml minus 1 t minus 2. There are three ways in which a fluid may change its dimension when an external force acts on it. There are shown in the figure 8.1. In the figure 8.1a, cylinder is stretched by two equal forces applied normal to its cross-section area. The restoring force per unit area in this case is called the tensile stress. If the cylinder is compressed under the action of applied forces, the restoring force per unit area is known as the compressive stress. Tensile or the compressive stress can be termed as the longitudinal stress. In both the cases, there is a change in the length of the cylinder. The change in the length delta L to the original length L of the cylinder, in this case is known as the longitudinal strain. So longitudinal strain is equal to the delta L by L. However, if two equal and opposite deforming forces are applied parallel to the cross-section area of the cylinder, as shown in the figure 8.1b, there is a relative displacement between the opposite faces of the cylinder. The restoring force per unit area developed due to the applied tangential force is known as the tangential or the shearing of stress. As a result of the applied tangential force, there is a relative displacement delta x between the opposite face of the cylinder as shown in the figure 8.1b. There is strain so produced is known as the shearing of strain and is defined as the ratio of the relative displacement of the face delta x to the strength to the length of the cylinder L. Shearing of strain is equal to delta x by L and equal to tan theta, where theta is the angular displacement of the cylinder from the vertical original position of the cylinder. Usually theta is very small, tan theta is nearly equal to the angle theta. If theta is equal to 10 degree, for example, there is only 1% difference between the theta and the tan theta. It can also be visualized when a book is pressed with the hand and pushed horizontally as shown in figure 8.2. Thus, the shearing of strain is equal to tan theta equal to 0 degree. In figure 8.1d, a solid of sphere placed in the fluid and the high pressure is compressed uniformly on all sides. The force applied by the fluid acts in the perpendicular direction at each point of the surface and the body is said to have another hydraulic compression. This leads to the decrease in its volume without any change of its geometrical shape. The body develops the internal restoring forces that are equal and opposite to the forces applied by the fluid. The body restores its original shape and the size when taken out from the fluid. The internal restoring force per unit area in this case is known as the hydraulic stress and in magnitude is known as the hydraulic pressure applied force per unit area. The strain produced by hydraulic pressure is called the volume of strain and is defined as the ratio of the change in the volume to the original volume. The volume of strain is equal to the delta P by V. Since the strain is the ratio of the change in the dimensions to the ordinal dimension, it has no unit for the dimensional formula. फिर आता है Hooke's law. The stress and the strain are take different forms in the situation depicted in figure 8.1. For a small deformity, the stress and the strain are proportional to each other. This is known as the Hooke's law. The stress is directly proportional to strain or stress equal to K into strain, where K is the proportionality constant and is known as the modulus of rigidity. Hooke's law is empirical law and is found to be valid for the most material. However, there are some materials which do not exhibit this linear relationship of stress of strain curve. The relation between the stress and the strain for a given material and the tensile of stress can be found experimentally. In a standard test of the tensile property, a test cylinder for our wire is stretched by a applied force. The fractional change in the length, the strain, and applied force needed to cause the strain are recorded. The applied force is usually increased in the steps and the change in the length is noted. A graph is plotted between the stress, which is equal to in magnitude to the applied force per unit area, and the strain produced. A typical graph for a metal is shown, analogous graph for the compression and the fear of stress may also be obtained. The stress of strain curve varies from the material to the material. These curves help us to understand how a given material deforms with increasing loads. From the graph, we can see that in the region between O to A, the curve is linear. In this region, Hooke's law is obeyed. The body regains its original dimension when the applied force is removed. In this region, the solid behaves like the elastic body. तो यहाँ पर जो typical stress of strain curve for the metal, ये हो गया strain, ये हो गया stress, ये हो गया yield point, ये हो गया proportional limit, ये हो गया fracture point, ये हो गया permanent fit. फिर आता है कि in the region A to B, stress and strain are not proportional. Nevertheless, the body still returns to its original dimension when the load is removed. The point B in the curve is known as the yield point, also known as the elastic limit, and the corresponding stress is known as the yield strength sigma pi of the material. If the load is increased further, the stress developed exceeds the yield strength, and the strain increases rapidly even for a small angle in the stress. The portion of the curve between the B and D for this when the load is removed, say at some point C between the B and D, the body does not regain its original dimension. In this case, even when the stress is zero, the strain is not zero. The material is said to have permanent fit. The deformation is said to be plastic deformation. The point D on the graph is the ultimate tensile strength of the material. Beyond this point, additional strain is produced even by the reduced applied force when the fracture occurs at the point D. If the ultimate of strength and the fracture at the point D and E are close, the material is said to be brittle. If they are far apart, the material is said to be the ductile. फिर यहाँ पर दिया हुआ है स्ट्रेस स्ट्रेस दिया हुआ 10⁶ न्यूटन पर मीटर स्क्वायर. यहाँ पर स्ट्रेन दिए हुए. The stress of strain curve for the elastic tube of the aorta, the large tube vessel carrying the blood from the heart का दिया हुआ है. इसको जो पूछ सकता है फिर इस ग्राफ को. नेक्स्ट है कि as stated earlier, the stress of strain behavior vary from the material to the material. For example, rubber can be pulled to several times its original length and still remains to its original shape. Figure 8.3 shows stress of strain curve for the elastic tissue of the aorta present in the heart. Note that although elastic energy region is very large, the material does not obey the Hooke's law over the most of the region. Secondly, there is no well-defined plastic region. Substances like the tissue of the aorta, rubber, etc., which can be stretched to cause large strain are called as the elastomers. फिर आता है elastic moduli. तो the proportional region within the elastic limit of the stress of strain curve, region OA, is of great importance for the structural and the manufacturing engineering design. The ratio of the stress of strain called the modulus of rigidity is found to be a characteristic of the material. अब बात करते हैं यंग मॉडुलस की. तो experimental observation show that for a given material, the magnitude of the strain produced is the same whether the stress is tensile or compressive. The ratio of the tensile or the compressive stress to the longitudinal strain is defined as the Young modulus and denoted by gamma. Gamma is equal to sigma by E. From the equation 8.1 and 8.2, we have gamma is equal to F by A and delta L by L, and F into L is equal by A into delta L. Since the strain is dimensional of quantity, the unit of the Young modulus is the same as that of the stress, Newton meter per meter square or Pascal. Table 8.1 gives the value of the Young moduli and the yield of strength of the submaterial. From the table data given in table 8.1, it is notified that for the metal, Young moduli are large. Therefore, these materials require a large force to produce the small length change in the length. To increase the length of a thin steel bar of 0.1 cm², cross-section area of 0.1%, a force of 2000 Newton is required. The force required to produce the same strain in the aluminum, brass and the copper bars having the same cross-section area are 690 Newton. 900 Newton, 1100 Newton respectively. It means that steel is more elastic than the copper, brass and aluminum. It is for this reason that the steel is preferred in a heavy-duty machine and in the structural region. The iron, wood, bone and the concrete and the glass have the rather a small young moduli. Next है कि structural steel rod has a radius of 10 mm and a length of 1 meter. If 4 kilonewton force of stretcher is along its length, calculate the stress, elongation and the strain on the rod. Young modulus of the structural steel is 2.0 × 10⁻11 Newton per meter square. तो B कहता है कि B assume that a rod is held by a clamp at one end and the force F is applied at the other end, parallel to the length of the rod. The stress on the force is stress equal to F by A and F by pi r square. The elongation is delta L is equal to F by L into gamma. यानी 1.59 mm. The strain is given by strain equal to delta L by L यानी 0.16%. नेक्स्ट है कि copper bar of length 2.2 meter and the steel bar of length 1.6 meter, both of the diameter 3 mm, are connected into the end when stretched by a load. The net elongation is found to be 0.4 mm. Obtain the load applied. So the copper end and the steel bar are under the tensile stress because they have the same tension equal to the load and the same area of the cross section. From the given tension, we have the stress is equal to strain into Young modulus. Therefore, W by H equal to gamma phi delta L by L and gamma F into delta F by LF, where the subscript phi and the F refer to the copper and the stainless steel respectively. तो यहाँ पर डेल्टा एल सी बाई डेल्टा एल एफ इक्वल टू गामा एफ बाई गामा फी इंटू एल सी इंटू एल एफ. तो गिवन एल सी इक्वल टू 2.2 मीटर एंड एल एफ इक्वल टू 1.6 मीटर. तो फ्रॉम अ टेबल गामा फी इक्वल टू 1.1 गुना 10⁻⁴ न्यूटन पर मीटर स्क्वायर, गामा फी इक्वल टू 2 गुना 10⁻⁴ न्यूटन पर मीटर स्क्वायर. तो डेल्टा एल सी बाई डेल्टा एल एफ इक्वल टू 2 गुना 10⁻11 बाई 1.1 गुना 10⁻11 गुना 2.2 बाई 1.6 यानी 2.5. The total elongation is given by delta LC by delta LC equal to 7 गुना 10⁻⁴. Solving the above equation, delta LC is equal to 5 गुना 10⁻⁴ and delta LF is equal to 2 गुना 10⁻⁴. Therefore, W equal to A गुना gamma phi by delta LC by LC यानी 1.8 गुना 1.8 गुना 10⁻² Newton. फिर आता है in the human pyramid in a circus, the entire weight of the balance group is supported by the legs of the performer who is lying on his back. The combined mass of all the person performing the act and the tables, plaques, etc. involved in the 40 kg. The mass of the performer lying on his back at the bottom of the pyramid is 40 kg. Each thigh bone femur of this performer has a length of 50 cm and effective radius of 2 cm. Determine the amount by which each thigh bone gets compressed under the extra load. तो ये ह्यूमन पिरामिड का दिखाया हुआ है. फिर इसमें आता है कि total mass of all the performers, yeah, tables plaque for the 240 kg, mass of the performer 50 kg. Mass supported by the leg for the performer at the bottom of the pyramid हो जाएगा 240 माइनस 50 यानी 220 kg. Weight of the supported mass हो जाएगा 220 kg weight यानी 220 गुना 9.8 यानी 2156 न्यूटन. Weight supported by each thigh bone of the performer हो जाएगा हाफ गुना 2156 is equal to 1073 न्यूटन. From the table 9.1, the Young modulus for the bone is given by gamma is equal to 9.4 गुना 10⁹ per meter square. Length of the thigh bone L is equal to 0.5 meter and the radius of thigh bone is equal to 2 centimeter. Thus the cross section area of the thigh bone A is equal to pi गुना 2 गुना 10⁻² minus 2 के स्क्वायर यानी जो 1.2 से गुना 10⁻³ minus 3 के मीटर के स्क्वायर. Using the equation 9.8, the compression in each thigh bone delta L can be found computed at delta L equal to F गुना L by gamma into A. तो आ जाएगा कितना 4.55 गुना 10⁻³ minus 3 centimeter. This is very small change. The fractional decrease in the thigh bone delta L by L आएगा 0.0091 or the 0.0091%. फिर आता है फेयर मॉडुलस. तो the ratio of the fairing of stress to the corresponding fairing of strain is called the fair modulus of the material and it corresponds to G. It is also called the modulus of rigidity. So G is equal to fairing of stress by fairing of strain. G is equal to F by A by delta X by L. So F into L by delta A into delta X. Similarly, from the equation 9.4 we have G is equal to F by A by delta theta. So F by A into theta. The fairing of the sigma can be also be expressed as sigma F is equal to G into theta. A fine unit of the fair modulus is Newton per meter square or Pascal. The fair modulus of a few common materials are given in table 9.2. It can be seen that fair modulus or modulus of rigidity is generally less than the Young modulus. For most materials, G is equal to gamma by 3. फिर एक क्वेश्चन है कि square lead slab of the side 50 cm and the thickness 10 cm is subjected to a fairing of stress on its narrow face of 9 गुना 4 Newton. The lower edge is riveted to the floor. How much will the upper edge be displaced? तो the lead slab यहाँ पर कहता है कि the lead slab is fixed and the force is applied parallel to the narrow face as shown in the figure 8.6. The force area of the parallel face to which this force is applied is 50 cm गुना 10 cm यानी 0.5 meter square. Therefore, the stress applied is 1.8 गुना 10⁻⁶ Newton per meter square. We know that fairing of strain delta X by L is equal to stress by G. Therefore, the displacement delta X is equal to stress into L by G. तो आ जाएगा 0.16 mm. Next, bulk modulus. So, in the section 8.3, we have seen that when a body is submerged in a fluid, it undergoes a hydraulic stress equal in magnitude to the hydraulic pressure. This led to the decrease in the volume of the body, thus producing a strain called the volume of strain. The ratio of the hydraulic stress to the corresponding hydraulic strain is called the bulk modulus. It is noted by the symbol B. So B is equal to minus P delta V by B. The negative sign indicates that the fact that with the increase in the pressure, a decrease in the volume occurs. Thus, that is, if the P is positive, delta V is negative. Thus, for a system in equilibrium, the value of the bulk modulus P is always positive. If unit of the bulk modulus is the same as that of the pressure, Newton per meter square or the Pascal, the bulk moduli of a few common materials are given in table 8.3. The reciprocal of the bulk modulus is called the compressibility and denoted by the K. It is defined as the fractional change in the volume per unit increase in the pressure. The K is equal to 1 by beta equal to minus 1 by delta P guna delta P by B. It can be seen from the table given in the table 8.3 that bulk moduli for the fluid are much larger than for the liquid, which are again much larger than the bulk moduli for the gaseous air. तो यहाँ पर दिया bulk moduli of the some common materials दिया हुआ है. पहले दिया हुआ है सॉलिड्स का, फिर दिया हुआ है लिक्विड्स का, फिर दिया हुआ है गैसेज का. नेक्स्ट आता है स्ट्रेस ऑफ स्ट्रेन एंड वेरियस इलास्टिक मॉडल दिया हुआ है. तो टेंसाइल और द कंप्रेसिव इज इक्वल टू होता है सिग्मा इज इक्वल टू एफ बाई ए ऑफ स्ट्रेस टू इक्वल एंड अपोजिट फोर्स परपेंडिकुलर टू द अपोजिट फेस. और शेयरिंग सिग्मा एफ इज इक्वल टू एफ बाई ए टू इक्वल एंड अपोजिट फोर्स पैरेलल टू द अपोजिट सरफेस. In the each case, that the total force and the total torque on the body vanishes. फिर hydraulic force is perpendicular to the everywhere to the surface force per unit area pressure same everywhere. फिर टेंस ये हो जाता है elongation और the compression parallel to the force direction delta L by L longitudinal strain. फिर होता है pure shear straight थीटा. ये होता है volume change compression और the elongation delta V by V. फिर उसके बाद चेंज इन द फेप. तो इसमें टेंसाइल और कंप्रेसिव में यफ होता है, शेयरिंग में भी होता है और हाइड्रोलिक में भी नहीं होता है. फिर चेंज इन द वॉल्यूम. तो टेंसाइल में नहीं होता है, शेयरिंग में नहीं होता है और हाइड्रोलिक में भी यफ हो जाता है. फिर इलास्टिक मॉडुलस गामा इक्वल टू एफ एल बाई ए बाई डेल्टा एल हो जाता है. जी इक्वल टू एफ बाई ए थीटा होता है और हाइड्रोलिक में होता है बी इक्वल टू माइनस पी डेल्टा बी बाई बी. इसका नेम ऑफ मॉडल स्विंग मॉडल, इसका फेयर मॉडल और मॉडल ऑफ रिजिडिटी, इसका बल्क मॉडल. जिसका होता है सॉलिड सॉलिड, इसका फुल लिक्विड एंड गैस हो जाता है. फिर इसमें आता है कि thus the solid for the least compressible, whereas the gases are the most compressible. Gases are about a million times more compressible than the solids. Gases have large compressibility which vary with the pressure and temperature. The incompressibility of the solid is primarily due to the tight coupling between the neighboring atoms. The molecules in the liquids are also bound with the neighbors but not as strong as in the solid. Molecules in the gases are very poorly coupled to their neighbors. Table 8.4 for that various types of the stress of strain, elastic moduli and the appreciable state of the matter lengths. The average depth of the Indian Ocean is about 10,000 meters. Calculate the fractional compression delta V by B of the water at the bottom of the ocean, given that the bulk modulus of the water is 2.2 × 10⁻⁹ Newton per meter square. So the pressure exerted by the 10,000 meter column of the water on the bottom layer P is equal to H rho G is equal to 3 × 10⁵ Newton per meter square. Fractional compression हो जाएगा delta V by B. तो delta V by B is equal to stress by B is equal to 1.36 × 10⁻⁻² equal to 1.36%. फिर आता है पॉइजन रेशियो. तो द स्ट्रेस परपेंडिकुलर टू द अप्लाइड फोर्स वी कॉल द lateral strain. Feynman Poisson pointed out that within the elastic limit, lateral strain is directly proportional to the longitudinal strain. The ratio of the lateral strain to the longitudinal strain is a stretched bar is called the Poisson ratio. In the original diameter of the bar is d, and the contraction of the diameter and the stress is delta d. Then the lateral strain is equal to delta d by b d. If the original length of the bar is L and the elongation under the stress is delta L, the longitudinal strain is delta L by L. Poisson ratio is then delta d by delta L by L or delta d by delta L. L by D Poisson ratio is the ratio of the two strains. It is a pure number and has no dimensions for the unit. Its value depends only on the nature of the material. For steel, the value is 0.28 and 0.30, and for aluminum alloy, it is about 0.33. फिर आता है इलास्टिक पोटेंशियल एनर्जी इन स्ट्रेचड बार. तो व्हेन अ बार इज पुट अंडर tensile stress, work is done against the interatomic forces. This work is stored in the bar in the form of the elastic potential energy. When a bar of the ordinal length L and area of cross-section A is subjected to a deforming force F along the length of the bar, let the length of the bar be longed by L. Then the force F is equal to gamma into 1 by L, where gamma is the Young modulus of the material of the bar. Now for the further elongation of the infinitesimal small length dl, work done dw is equal to f dl or gamma L dl by L. Therefore, the amount of the work done w in the increasing the length of the bar from L to L plus L is, that is 0 to L plus L is equal to w is equal to half into of stress into strain into volume of the bar. This work is stored in the form of the elastic potential energy U. Therefore, the elastic potential energy per unit of the bar is U is equal to half sigma into E आ जाएगा. फिर आता है applications of the elastic behavior of the material. The elastic behavior of the material plays an important role in everyday life. All engineering design require precise knowledge of the elastic behavior of the material. For example, while designing a building, The structural design of the columns, beams, and the supports require knowledge of the strength of the material fluid. Have you ever thought why the beam fluid in the construction of bridges and supports etc. have a cross section of the type I? Why does a heap of the sand or a hill have a pyramidal shape? Answer to these questions can be obtained from the study of the structural engineering, which is based on the concept developed here. यहाँ पर दिया है कि cranes used for the lifting and moving heavy loads from the one place to another have a thick metal rope to which the load is attached. The rope is pulling up using the pulley and the motor. Suppose you want to make a crane which has lifting capacity of 10 tons or the metric tons. 1 metric ton is equal to 1000 kg. How thick should the steel rope be? We obviously want that the load does not reform the rope permanently. Therefore, the extension should not exceed the elastic limit. From the table 8.1, we find that mild of steel has a yield of strength of the 3000 गुना 6 Newton per meter square. Thus, the area of the cross section of the rope should be at least A should be greater than W by sigma by यानी mg by sigma by यानी 3.3 गुना 10 minus 4 meter square, corresponding to a radius of about 1 centimeter for a rope of circular cross section. Generally, a large margin of the safety of a factor of 10 in the load is provided. Thus, a thicker rope of the radius of 3 cm is recommended. A single bar of this radius would practically be a rigid rod, so the ropes are always made of the number of the thin bars braided together, like in the pigtails or for engine manufacture, flexibility and strength. A bridge has to be designed so that it can withstand the load of the flowing traffic, the force of the winds and its own weight. Similarly, in the design of the building, the use of the beams and the columns is very common. In both the cases, the overcoming of the problems for the bending of the beams under a load is prime importance. The beam should not bend too much or break. Let us consider the case of the beam loaded at the center and the supported near its end, as shown in the figure 8.6. A bar of the length L, breadth B, and the depth D being loaded at the center of the load W facts by an amount given by delta is equal to WLQ by 4B dq into gamma. A beam supported at the ends and loaded at the center पर जो दिखाया हुआ है. नेक्स्ट आता है कि this relation can be derived using what you have already learned from little calculus. From the equation 8.1 we see that to reduce the bending of a given load, one should use a material with a large Young modulus gamma. For a given material, increasing the depth d rather than the breadth b is more effective in reducing the bending, since delta is proportional to d के power minus 3 and only b के power minus 1. Of course, the length L of the span should be as small as possible, but on increasing the depth, unless the load is exactly at the right place, difficult to arrange in a bridge with moving traffic, the deep bar may bend as shown in the figure 8.1b. This is called buckling. To avoid this, a common compromise is the cross-section shape shown in the figure 8.1c. This section provides a large load bearing surface and enough depth to prevent the bending. This shape reduces the weight of the beam without sacrificing the strength and hence reduces the cost. तो यहाँ पर देखो different cross section shape of a beam, rectangular section of a bar, a thin bar, and how it can buckle. Commonly used section of a load bearing bar. The use of the pillar for the columns is also very common in the buildings and the bridges. A pillar with a rounded end as shown in figure 8.9a supports less load than with the distributed shape at the ends. The preferred design of a bridge or a building has to take into account the condition under which it will function, the cost and the long period reliability of the usable material, etc. फिर दिया हुआ है यहाँ पर दिया हुआ है पिलर फॉर द कॉलम्स, पिलर राउंडेड विद ends and pillar with the distributed ends here दिखाया हुआ है. The answer to the question why the maximum height of the mountain on the earth is 10 km can also be provided by considering the elastic property of the rock. A mountain base is not under the uniform compression, and this provides the some shearing of stress to the rocks under which they can flow. The stress due to all the material on the top should be less than the critical shearing of stress at which the rock flow. At the bottom of the mountain of the height h, the force per unit area due to the weight of the mountain is h rho g, where rho is the density of the material of the mountain and g the friction due to gravity. The material at the bottom experiences this force in the vertical direction, and this side of the mountain are free. Therefore, this is not a case of the refer or the bulk compression. There is a shear component approximately h rho g itself. Now the elastic limit for a typical rock is 30 गुना 10 power 7 Newton per meter square. You get this to the h rho g, while rho is equal to 3 गुना 10 power 10 kg per meter cube gives the h rho g equal to 30 गुना 10 power 7 Newton per meter square. h is equal to 30 गुना 10 power 7 Newton per meter square और by 3 गुना 10 power 3 गुना by 10 यानी कितना आएगा 10 किलोमीटर, which is more than the height of the mount. ठीक है, इसका आगे फिर इसका समरी है. तो स्ट्रेस इज द स्ट्रेइंग फोर्स पर यूनिट एरिया एंड स्ट्रेन द फ्रैक्शनल चेंज इन द डायमेंशन. इन जनरल देयर आर 3 टाइप्स ऑफ द स्ट्रेस: टेंसाइल स्ट्रेस, longitudinal stress, stress with the stretching, or the compressive stress distributed with the compression, shearing of stress, and hydraulic of stress. For the small deformation of stress is directly proportional to the strain. For many material, this is known as the Hooke's law. The constant for the proportionality is called the modulus of the elasticity. Three elastic moduli, namely the Young modulus, shear modulus, or the bulk modulus, are used to describe the elastic behavior of the object as they respond to the deforming of stress that act on them. A class of the fluid called elastomer does not obey the Hooke's law. When an object is under the tension or the compression, the Hooke's law takes the form of F by H equal to gamma delta L by L. When the delta L by L is the tensile or the compressive strain of the object, F is the magnitude of the applied force causing the strain, A is the cross-section area over which the F is applied, perpendicular to the A, and gamma is the Young modulus of the object. The stress is F by A. A pair of the force when applied to the parallel to the upper and the lower forces, the fluid deforms so that the upper face remains smooth sideways with respect to the lower. The horizontal displacement delta L of the upper face is perpendicular to the right vertical height L. This type of deformation is called the shear, and the corresponding of stress is shearing of stress. This type of stress is present only in the solid. In this kind of the deformation, the Hooke's law takes the form F by A equal to G delta L by L, where delta is the displacement of the one end of the object in the direction of the applied force F, and the G is the shear modulus. When the object undergoes the hydraulic compression due to the stress exerted by the surrounding fluid, the Hooke's law takes the form B P is equal to B delta V by B, where P is the preferred hydraulic stress on the object due to the fluid. Delta V by B is the volume of strain due to the fluid fractional change in the object volume due to the pressure, and B is the bulk modulus of the object. अब यहाँ पर कुछ इंपॉर्टेंट पॉइंट्स हैं, जैसे in the case of the bar suspended from the ceiling and stretched under the action of a bait F suspended from its other end, the force exerted by the ceiling are equal and opposite to the bait. However, the tension and cross section A of the bar is just F and not 2F. Hence, the tensile stress which is equal to the tension point area is equal to F by A. Hooke's law valued only in the linear part of the stress of strain curve. The Young modulus and the shear modulus are relevant only for the solid. Since only solids have the length and the shape. Bulk modulus element for the solid, liquid, and the gaseous. It refers to the change in the volume when every part of the body is under the uniform stress, so the shape of the body remains unchanged. Metals have large volume of the value of the Young modulus than the alloy and the elastomers. A material with large value of the Young modulus requires a large force to produce a small change in its length. In daily life, we feel that material which stretch more is more elastic, but it is a misnomer. In fact, material which stretches to a lesser extent to a given load is considered to be more elastic. यहाँ से बहुत ही अच्छा स्टेटमेंट ये जो बनाया जा सकते हैं. Next, in general, a deforming force in the one direction can produce a strain in the other direction. Also, the proportionality between the stress and the strain in which the friction cannot be described by just one elastic constant. For example, for a bar under the longitudinal strain, the lateral dimension radius of the cross section will undergo a small change, which is described by another elastic constant of the material called the Poisson ratio. A stress is not a vector quantity. Unlike force, the stress cannot be assigned a specific direction. Force acting on the portion of the body on the preferred side of a section has a definite direction. अब कुछ क्वेश्चन है, जैसे ए स्टील बार ऑफ द लेंथ 4.1 मीटर एंड द क्रॉस सेक्शन एरिया ऑफ द 3 × 10⁻⁵ मीटर स्क्वायर स्ट्रेचड बाय द सेम अमाउंट एट द कॉपर बार ऑफ द लेंथ 3.5 मीटर एंड द क्रॉस सेक्शन एरिया ऑफ द 4 × 10⁻⁵ मीटर स्क्वायर एंड a given load. तो what is the ratio of the Young modulus of the steel to that of the copper? तो लेंथ ऑफ द स्टील बार L1 इक्वल टू 4.1 दिया हुआ है. एरिया ऑफ द क्रॉस सेक्शन ऑफ द स्टील बार A1 इक्वल 3 × 10⁻⁵ मीटर स्क्वायर. लेंथ ऑफ द कॉपर बार L2 इक्वल 3.5 मीटर दिया हुआ है. तो एरिया ऑफ द क्रॉस सेक्शन ऑफ द कॉपर बार A2 इक्वल टू 4 × 10⁻⁵ मीटर स्क्वायर हो जाएगा. तो चेंज इन लेंथ डेल्टा L1 इक्वल डेल्टा L. तो फोर्स अप्लाइड इन बोथ केस हो जाएगा F. तो गामा U1 इक्वल टू L1 बाई डेल्टा L. तो आ जाएगा कितना. और यंग मॉडुलस ऑफ द कॉपर बार गामा U2 इक्वल टू F2 बाई A2 L2 बाई डेल्टा L2. तो इतना आ जाएगा. डिवाइडिंग 1/2 गेट 1.49:1 आ जाएगा. तो यंग मॉडुलस ऑफ द स्टील टू द कॉपर कितना आ जाएगा 1.49:1. नेक्स्ट है figure 9.11 for the stress of strain curve for a given material. What are the Young modulus and the approximate yield strength of the material? It is clear from the given graph that stress 150 × 6 Newton per meter square of strain is 0.002. Young modulus gamma equal to stress by strain. तो 1.150 × 6 by 0.02 equal to 7.5 × 10 Newton per meter square. Hence, the Young modulus for the given material is 1.5 × 10 Newton per meter square. The yield strength of the material is the maximum of stress that the material can sustain without crossing the elastic limit. It is clear from the given graph that approximate yield of strength of this material 3 Newton per meter square और 3 × 8 Newton per meter square. फिर आता है कि the stress of strain curve for material A and B are A का दिया B का दिया. The graph are drawn to the same scale. Which of the following has the greater Young modulus? Which of the two is the stronger material? तो for a given strain, the stress for the material A is more than for the material B as shown in the graph. The Young modulus is equal to the stress by strain. For a given strain, If the stress for a material is more than the Young modulus is also greater for that material, therefore the Young modulus of material is greater than that it is for the material B. The amount of the stress required for fracturing a material corresponding to its fracture point gives the strength of that material. Fracture point is the extreme point in the stress strain curve. It can be observed that material A can be withstand more strength than material B, and this material A is stronger than the material B. फिर आता है कि read the following true statement below carefully and state the reason if it is true or false. The Young modulus of the rubber is greater than that of the steel. Or the fact the stretching of a coil is determined by the shear modulus. So for a given stress, the strain in the river is more than the steel. तो Young modulus is equal to gamma equal to stress by strain. For a constant stress, gamma जो होता है इन्वर्सली प्रोपोर्शनल टू स्ट्रेन होता है. Hence the Young modulus of the rubber is less than that for the steel. Shear modulus is the ratio of the applied stress to a change in the shape of the body. The stretching of the coil changes its shape. Hence the shear modulus of the left is involved in this process. Next question है कि two bars of the diameter 0.25 centimeter, one made of the steel and the other made of the brass are loaded as shown in the figure 9.13. The unloaded length of the steel bar is 1.5 meter and that of the brass bar is 1 meter. Compute the elongation of the steel and the brass bar. So elongation of the steel bar 1.49 गुना 10 minus 4 meter. Elongation of the brass bar 1.3 गुना 10 minus 4 meter. So D is equal to 0.25. So D equal to R equal to D by 2 0.125. तो लेंथ ऑफ द स्टील बार L1 इक्वल टू 1.5, लेंथ ऑफ द ब्रास बार L2 इक्वल टू 1 मीटर हो जाएगा. तो टोटल 450 जो स्टील बार हो जाएगा 6 प्लस 4 को 10 9.8 यानी 98 न्यूटन. तो गामा 1 इक्वल टू हो जाएगा F1/A1 यानी डेल्टा L1/L. तो डेल्टा L1 फोर्स चेंज इन द लेंथ ऑफ द स्टील बार हो गया और A1 जो हो गया एरिया ऑफ द क्रॉस सेक्शन ऑफ द स्टील बार पाई R1 का स्क्वायर हो गया. तो एक मॉडुलस ऑफ द स्टील गामा 1 इक्वल टू 2 गुना 10⁻11 पास्कल. तो डेल्टा 1 इक्वल टू निकालेंगे तो इतना आ रहा है 1.49 गुना 10⁻4 मीटर. टोटल फोर्स ऑन द ब्रास पर हो जाएगा F2 इक्वल टू 9.8 यानी 58.8 न्यूटन. तो यंग मॉडुलस फॉर द ब्रास हो जाएगा गामा 2 इक्वल टू F2/A2 यानी डेल्टा L2/L2 वेयर द डेल्टा L2 चेंज इन द लेंथ A2 इज द एरिया ऑफ द क्रॉस सेक्शन ऑफ द ब्रास बार. तो डेल्टा इक्वल टू F2 गुना L2/A2 गुना L2 गामा 2 तो जाएगा 1.3 गुना 10⁻4 मीटर. तो इलोंगेशन ऑफ द स्टील बार 1.49 गुना 10⁻4 मीटर और इलोंगेशन ऑफ द ब्रास बार आ जाएगा 1.3 गुना 10⁻4 मीटर. नेक्स्ट है the edge of the aluminum cube is 10 cm long. One face of the cube is firmly fixed to a vertical ball. A mass of the 4 kg is then attached to the opposite face of the cube. The shear modulus of aluminum is 25 G Pascal. What is the vertical deflection of this face? So edge of the aluminum cube L is equal to 10 cm 0.1 meter. Mass of the attached cube M is equal to 4 kg. Shear modulus of the aluminum is equal to 25 G Pascal and 25 गुना 10⁻9 Pascal. तो shear modulus is equal to shear stress by shear strain F by A L by delta L. तो F जो होता है अप्लाइड फोर्स mg इक्वल टू 940 न्यूटन. ए जो एरिया ऑफ द फेस 0.1 0.001 मीटर स्क्वायर. डेल्टा एल जो होगा वर्टिकल डिफ्लेक्शन ऑफ द क्यूब. तो डेल्टा एल इक्वल टू एफ एल बाई ए ईटा तो आएगा 3.9 गुना 10⁻7 मीटर. तो वर्टिकल डिफ्लेक्शन ऑफ द फेस हो जाएगा 3.9 गुना 10⁻7 मीटर. अगला सवाल 4 identical hollow cylindrical column for the mild steel support a big structure of the mass 50,000 kg. The inner and the outer radius of each column are 3 cm and 50 cm respectively. Assuming the load distribution to be uniform, calculate the compression strain of the each column. तो in mass of the bigger structure m equal to 50,000 kg. Inner radius of the column gam r equal to 3 cm 0.3 meter. Outer radius of column r equal to 50 cm 0.6 meter. The young modulus of the steel gamma equal to 2 गुना 10⁻11 पास्कल. टोटल पर फोर्टेड ई फ्री इक्वल टू एम इक्वल टू 50,000 गुना 9.8 तो आएगा 12,000. ठीक है इतना आ जाएगा. तो यंग मॉडुलस होता है स्ट्रेस बाय स्ट्रेन हो जाएगा एफ. स्ट्रेन होता है एफ बाई इंटू गामा. तो एरिया दिया हुआ है पाई आर के स्क्वायर माइनस आर के स्क्वायर यानी पाई गुना 0.6 स्क्वायर माइनस 0.3 के स्क्वायर. तो कितना आएगा 7.22 गुना 10⁻7. हेंस द कंप्रेशन ऑफ स्ट्रेन ऑफ द ईच कॉलम हो जाएगा 7.22 गुना 10⁻7. नेक्स्ट है a piece of the copper having a rectangular cross section area of 15.2 mm and 19.1 mm is pulled in the tension with 44,500 Newton force producing only elastic deformation. Calculate the resulting strain. तो length of the piece of the copper हो जाएगा L equal to 19.1 mm यानी 9.1 गुना 10⁻10 मीटर. Breadth of the piece of the copper हो जाएगा B equal to 15.2 mm 15.2 गुना 10⁻3 मीटर. तो area of the copper bar piece हो जाएगा A equal to L into B. तो इतना आ जाएगा यानी 2.9 गुना 10⁻4 मीटर स्क्वायर. टेंशन फोर्स अप्लाइड बाय द पीस ऑफ द पेपर इफ इक्वल टू 44,500 न्यूटन आ जाएगा. तो मॉडुलस ऑफ इलास्टिसिटी ऑफ द कॉपर हो जाएगा N2 इक्वल टू 42 गुना 10⁻9 मीटर स्क्वायर. तो स्ट्रेन हो जाएगा F बाई ए ईटा यानी 3.65 गुना 10⁻3. नेक्स्ट है steel cable with a radius of 1.5 cm supports a chair lift at sky area. If the maximum of steel is not to fit the support at Newton per square, but the maximum load the cable can support. तो द radius of the steel bar r is equal to 1.5 centimeter, 0.015 meter. Maximum alloy stress equal to F over r Newton per meter square. Maximum stress equal to maximum force by area of the cross section. तो maximum force equal to maximum stress गुना area of the cross section, यानी 10 के ऊपर 8 गुना पाई गुना 0.015 square, यानी 7.065 गुना 10 4 न्यूटन. तो आंसर आएगा 7.065 गुना 10 4 न्यूटन. Glove wall. A rigid bar of the mass 15 kg supported symmetrically to the three bars, each of the 2 meter long, those at each end are copper and the middle one is iron. Determine the ratio of their diameter if each is to be have the same tension. The tension of the force acting on each by the same, the tension in each by the same. Hence, since the bar for the same length, the strain will also be the same. So gamma is equal to stress by strain and F by strain. तो 4F by pi d square into strain. F जो है टेंशन फोर्स, ये जो है एरिया ऑफ द क्रॉस सेक्शन, जो diameter of the bar. It can be said that gamma directly proportional to 1 by d square. The young modulus for the iron gamma is equal to 1/10⁹ Pascal. Diameter of the bar d1 हो जाएगा. Young modulus of the copper gamma 2 equal to 1/10⁹ Pascal. Diameter of the copper bar d2 हो जाएगा. तो यहाँ पर d2 by d1 हो जाएगा रूट ओवर गामा 1 गामा 2, यानी 1.31:1 आ जाएगा. फिर आता है कि a 14.5 kg mass fastened to the end of a steel bar of the unstretched length 1 meter is welded in a vertical circle with an angular velocity of the 2 revolutions per second at the bottom of the circle. The cross-section area of the circle wire is 0.065 centimeter square. Calculate the elongation of the bar when the mass is at the lowest point of the path. So m is equal to 14.5 kg. Length of the steel bar L is equal to 1 meter. Angular velocity omega is 2 revolutions per second. Cross-section area of the bar A is equal to 0.065 centimeter square. Let delta L be the elongation of the bar when the mass is at the lowest point of its path. When the mass is placed at the position of the vertical circle, the total force on the mass is equal to F is equal to mg by ml omega square, यानी 200.1 न्यूटन. तो यंग मॉडल हो जाएगा स्ट्रेस बाय स्ट्रेन. तो यहाँ पे डेल्टा एल इक्वल टू होगा एफ एल बाई ए गामा. नेक्स्ट है यंग मॉडल ऑफ द स्टील बार 2 पास्कल. तो डेल्टा इज इक्वल टू 1.539 4 मीटर. यहाँ से लॉन्गेशन ऑफ द बार हो जाएगा 1.539 4 मीटर. अगला सवाल. Compute the bulk modulus of the water from the following data. Initial volume 4 liter, preferred in case 4 atm, 1 atm 1.013 गुना 5 पास्कल. Final volume 4.5 liter. Compare the bulk modulus of the water with that of the air at the constant pressure. Explain in the simple terms by the ratio is so large. तो initial volume V1 equal to 4.1, यानी 100 गुना 4 minus 3 meter cube. Final volume H equal to 4.5 गुना 4 minus 3 meter cube. तो delta V equal to V2 minus V equal to 0.5 गुना 4 minus 3 meter cube. Bulk modulus delta P by delta B by V1 आएगा 2.026 गुना 9 पास्कल. तो बल्क मॉडुलस ऑफ एयर होता है 1 गुना 5 पास्कल. तो यहाँ पे करेंगे तो आएगा 2.026 गुना 4 तो दिस रेशियो इज वेरी हाई बिकॉज ऑफ इट एयर इज मोर कंफर्टेबल देन द वाटर. अगला सवाल है कि वाट इज द डेंसिटी ऑफ द वाटर एट डेप्थ वेयर द water density of water at depth where the preferred 80 meter 80 atm given that the density at the surface is 1.013 units per 3 kg per meter cube. So let the height of the depth, let the given depth pH prefer at the given depth pH equal to 80 atm and F गुना 1.01 गुना 5 pascal. Density of the water P1 is equal to 1.013 गुना 3 kg per meter cube. Let rho to be the density of the water at the height depth H. P1 with the volume of the water of the mass m at the surface, V2 with the volume of the water of the mass m at the depth H. Let delta V with the change in the volume, तो delta V V1 minus V2 यानी m 1 by rho 1 minus 1 by rho 2. तो volume of strain हो जाएगा delta V by V यानी m 1 by rho 1 minus 1 by rho 2 rho L by m. तो delta V by V1 हो जाएगा 1 minus rho 2. Delta bulk modulus P equal to rho V 1 by delta L. तो delta V by V rho by B. तो compressivity of the water हो जाएगा 1 by बीटा यानी 45.8 गुना 10 minus 11 पास्कल. तो डेल्टा वी बाई वी वन हो जाएगा कितना 3.1 होगा तो 4 -3. तो फॉर्म द इक्वेशन 1 and 2 we get 1 minus rho 1 by rho 2 equal to हो जाएगा 1.034 गुना 3 kg per meter क्यूब. Therefore the density of the water at given at H equal to 1.034 गुना 3 kg per meter क्यूब. अगला है कैलकुलेट द फ्रैक्शनल चेंज इन द वॉल्यूम ऑफ ए ग्लास स्लैब व्हेन सब्जेक्टेड टू हाइड्रोलिक प्रेशर ऑफ 10 atm. तो हाइड्रोलिक प्रेशर एक्सर्टेड बाय द ग्लास स्लैब P is equal to 10 atm, therefore 1.013 गुना 5 पास्कल. Bulk modulus of glass B equal to 35 गुना 9 meter per square. Bulk modulus B equal to P into delta B by B. तो delta B by फ्रैक्शनल चेंज इन वॉल्यूम है तो delta B by B equal to P by B to 2.13 गुना 4 minus 5 पास्कल आ जाएगा. Hence the fractional change in the volume of the glass slab 2.13 गुना 4 minus 5 पास्कल. Next, determine the volume of the contraction of a fluid copper cube 10 cm on the edge when the fluid to hydraulic pressure of 7.0 गुना 6 पास्कल. तो लेंथ ऑन द एज ऑफ द fluid copper cube L is equal to 10 cm यानी 0.1 मीटर. हाइड्रोलिक प्रेशर P is equal to 7 गुना 6 पास्कल. बल्क मॉडुलस ऑफ कॉपर B is equal to 140 गुना 9 पास्कल. तो बल्क मॉडुलस P बीटा is equal to P डेल्टा B by B. तो डेल्टा B by B वॉल्यूमेट्रिक स्ट्रेंथ, डेल्टा B चेंज इन द वॉल्यूम, B जो ओरिजिनल वॉल्यूम हो गया. डेल्टा B हो जाएगा PV by बीटा फाइनल वॉल्यूम ऑफ द क्यूब भी एल क्यू हो जाएगा, तो डेल्टा भी इक्वल टू पी एल क्यू वाई बीटा हो जाएगा। तो आंसर आएगा 5 गुना 10 माइनस 2 सेंटीमीटर। देयरफॉर द वॉल्यूम कंडक्शन ऑफ द फ्लूइड कॉपर हो जाएगा 5 गुना 10 माइनस 2 पर सेंटीमीटर क्यूब। फिर आता है कि हाउ मच द प्रेशर ऑन द लीटर ऑफ द वाटर विच चेंज टू कंप्रेस्ड बाय 0.1%, 0.10% है। तो वॉल्यूम ऑफ द वाटर भी इक्वल टू 1 लीटर, इट इज गिवन दैट वाटर टू बी कंप्रेस्ड बाय 0.10%। तो फ्रैक्शनल चेंज होगा डेल्टा भी वाई भी, यानी 0.1 बाई 4 गुना 1 10 पर माइनस 3। तो बल्क मॉडल ऑफ बी इक्वल टू रो डेल्टा भी वाई भी, तो पी इक्वल टू बी डेल्टा भी वाई भी। तो बल्क मॉडल फॉर वाटर इक्वल टू 2.2 गुना 10 माइनस 9 न्यूटन पर मीटर स्क्वायर। तो पी इक्वल टू 2.2 गुना 9 गुना 10 माइनस 3, यानी 2.2 गुना 6 न्यूटन पर मीटर स्क्वायर। Therefore the pressure of the water fluid 2.2 गुना 6 न्यूटन पर मीटर स्क्वायर। तो यहाँ पर जो चैप्टर ये कंप्लीट होता है। सही है।